video. This is Mrs. Pausing. I'm going to go through these Unit 6 Day 2 notes on rational functions and expressions. Just kind of quickly give you an overview of what we talked about in class today. So first we'll start with definitions of what is a rational expression or function. Then we'll talk about finding domain and for rational functions, which will lead us into vertical asymptotes, and then we will talk about horizontal asymptotes, and then we'll talk about whole figures. Okay? So kind of about, it's 5-ish parts to these notes. So first, let's talk about our definition. We need to get straight here. Rational expressions. A rational expression, all it is when you have a fraction with a polynomial in the numerator and a polynomial in the denominator. So for example, you can think of it as y equals, a polynomial in the numerator divided by a polynomial in the denominator. And it can be a y equals, it can also be f of x equals. It doesn't matter. But the main point is it's a polynomial divided by a polynomial. Now, there's a couple things that you cannot have and have a rational expression. One is you cannot have no fractional exponents. Can't have that. So for example, if we look down here at the second example here, you'll see you have a fractional exponent. So this is a fractional exponent. Exp. So this is not a rational expression. Okay? Alright, another thing you cannot have is you cannot have any exponential functions. So for example, you cannot have, like here in this third example, we have an exponent with an x. This is not a rational expression. This is an exponent as a variable as an exponent. Exponent is a variable. Okay, that's also called an exponential function. Okay, so that's not a rational exponent. And lastly, you really just can't have any weird things, right? You also cannot have any like absolute value bars. Abbreviate this, ABS value. So for example, in this fourth example here, we have absolute value bars, right? So this is not a rational exponent because of the absolute value bars. This is absolute value, so not rational. Sorry, not a rational expression. Alright, so that leaves us with these last two. This first example here in green, this is a rational expression of a polynomial divided by a polynomial. And this last example, this is a rational function, again, because we're polynomial over polynomial. And while this doesn't look like a polynomial, it actually is a polynomial. This is a monomial, which is a polynomial. Okay? So it's a polynomial divided by two binomials, which actually, when you FOIL it out, would be a trinomial. But anyways, that is actually a polynomial divided by a polynomial. Alright, so I got our definitions about what rational expressions are and rational functions. These are all rational functions because they have f of x equals. F of x equals something. A rational expression, remember, you just don't have that equal sign. It's just an expression. It's not equal to y. It's not equal to x. Or, sorry, not equal to f of x. Okay, so let's go to the next section. So that's the definitions. So now we want to talk about finding domain of rational functions. So to find domain of rational functions, there's two ways you can do this: in the calculator, or you can do it by looking at the your denominator. So let's talk about the calculator way first. Calculator way, pull up my calculator. We'll just do this first example. Maybe calculator turn on. So y equals, and I'm just going to type it in exactly as I see it. The first example, A, is 5x squared minus 8x plus 2. And then I'm going to put my denominator in parentheses, dividing by x minus 4. Okay, so I just typed in my calculator and then I pushed graph. Alright, so you'll notice that this graph, it comes up, it has this vertical line at x equals 4. Well, that's a vertical asymptote. Okay, it's a vertical asymptote. So We'll get to asymptotes in a second. Right now we're just really working on what our domain is. So my domain is all real numbers except for where I see this vertical line at x equals 4. So the way we would write that is, there's a couple ways. One way we can write domain equals all real numbers such that x does not equal 4, which is where my asymptote is. Or we could write it as negative infinity to 4, not including 4, so I'll use parentheses. And union also from 4, not including it, so I use parentheses, to positive. So basically all real numbers except for 4. Okay, so 2 ways to write it. Either way is fine. But a couple things you want me to notice is, notice that this 4, how it relates to our denominator. Okay, because that's important for how you actually find your domain by looking at the graph, or by hand rather than just looking at the graph. So for this first one, we just looked at the graph and we saw it looks like this. Down here. Okay, it looked like this, and we had this vertical line at x equals 4. And then parabola, it looks like that. Okay? That means this graph includes everything except for 4. Alright? So that was how we found it in the calculator. Now let's talk about how we find it when we're not looking at the calculator. So when we're not looking at the calculator, and we're doing this by hand, it's blue, I can take my denominator, and the domain is all real numbers except where this equation is, or function is undefined. Undefined is, you know a function is undefined where its denominator equals 0. Okay? So it's undefined where its denominator, I'll write this out, equals 0. So we can find where the denominator equals 0, so I can take x plus 1, set it equal to 0, minus 1 for both sides, x equals negative 1. My denominator is undefined at x equals negative 1. That also means my domain does not includes all real numbers except for negative 1. So I could write this as, my domain includes all real numbers such that x does not equal negative 1, okay? It's undefined at negative 1. Also, if I were to graph it, I would see that there's a vertical asymptote at x equals negative 1. Okay, but we'll get to that more on the next screen. But, so there's two things we can determine based on having where our graph or function is undefined. The first thing is we can find our domain. The second thing is we can find our vertical asymptote. It can be abbreviated VA, but we also can find our vertical asymptote. We'll talk about this more on the next page of notes. Our vertical asymptote is x equals negative 1. Okay? And we also find our domain. Okay? That is what we can find by determining where our graph is undefined. Okay? So, two things we can find. Now, remember, what that means is, if we look back at this first example, I have a vertical asymptote, abbreviated VA, at x equals 4, right? That means that my graph touches all numbers except for x equals 4. That's what a vertical asymptote is. It's just a line at which your graph does not cross or doesn't touch. Okay, that's what vertical asymptote is. Okay, so that one is B. Alright, so C, again, let's just look at C real quick. Let's do this by hand because it's faster by hand than typing this in your calculator. But I have vertical asymptotes where my denominator is undefined. My denominator is undefined where my denominator equals 0. So I start by setting my denominator equals 0. When I set my denominator equals 0, I need to solve for x. Well, to get rid of this 5, I'm going to take the fifth root of both sides. Don't really have to do this because we know that anything times or fifth root of 0 or anything is just going to be 0, so this will be x equals 0. So I have a domain. So I know I have a vertical asymptote at x equals 0, but I also know my domain is all real numbers such that x does not equal equal 0. Okay? All real numbers. Okay? Such that x does not equal 0. I also know that I have a vertical asymptote, VA stands for vertical asymptote, at x equals 0. Okay? So the two things I know by finding out where my denominator equals 0. Alright, so let's go down to this bottom section. I'm erasing this, but if you need to see it, you can always pause the video and go back. Okay, so the bottom section down here, again, I just need to find where my denominator equals 0. Once I find that, then it can tell me what my domain is, and it can tell me what my vertical asymptotes are. Alright, so where my denominator equals 0. Here, though, I have two factors. I need to set both of them equal to 0. So I have x plus 6 equal to 0. So I will have two asymptotes, or rather two vertical asymptotes. I have 3x minus 1 equals 0. Okay? So just solve for x. This gives me x equals to -6. And this one gives me x equals a third. So I also now know that my domain, I can figure out two things from where my denominator is undefined. I can figure out my domain, and I can figure out my vertical asymptote. So my domain is all real numbers such that x does not equal where my denominator is undefined, which is -6, and x does not equal 1/3. Okay? Or another thing I can figure out are also my vertical asymptotes. I know my vertical asymptotes are where my denominator is undefined. So I have vertical asymptotes at x equals -6, and I have vertical asymptotes at x equals, you write that, at x equals 1/3. Okay, so I have two vertical asymptotes, and also my domain doesn't touch those lines, which makes sense, right? My domain is everything except for my two vertical asymptotes, because my line doesn't actually cross those vertical asymptotes. Okay, so now we go to E. So E has a little bit extra step. Okay, same thing though. I want to know where my denominator is equal to 0, because where it's undefined, where it's equal to 0 is where it's undefined. Where it's undefined tells me my domain and my vertical asymptotes. However, notice in D, it was already factored for me, and I just set my two factors equal to 0 and solved it. Well, E is not already factored for me, so I need to factor E. Now, we learned in class how to use our calculator to factor. And unfortunately, the calculator that I have on my computer does not have that app. But remember, we go to apps, so I'll write the steps out and you can follow them along and come and see me if you have questions about this. It's just typing in your calculator. But this purple button where the little cursor is on this calculator, it's purple, it says apps in purple. That's what you're going to push. When I say apps, that's what I'm referencing. So to factor, so we need to factor this first. So we're going to factor with our calculator. Okay, you can factor by hand, but I want to make sure that people are struggling with factoring can still get to the answer here. So factor in the calculator. First, you're going to push the apps button. Okay, I'll write out the steps so you have them for your notes and come see me go over it. Then you push number 9, which says, looks like Plysmith, but what it stands for is Poly Simulator. It's like SMTH or something like that. And then you push number 1, which is like Rube Simulator or something. I think it's this one with the Rube. Then you put in your, it'll say like A2, A1, A0. Okay, this is basically our A, B, and our C, right? When we're doing a quadratic formula, it's our A, B, and C. Okay, so my A is a 2, that's right here. My B is a -11, that's right here. And my C is a -40, okay? So if I push those in, and then I push, you push the graph button, you'll notice right above the graph button, there's a little box that looks like this on the screen, and it says like next or solve or something like that. So that's what you push. Okay, so but it's actually the graph button is what you're pushing. Okay, and then you'll push. I think then it'll give you your final answers. Okay, it'll spit out something that says like x1 equals x2 equals, okay? These are your zeros. That's what it's giving you because you're factoring. So remember, you factor, you get zeros. And it will give you x equals negative 5 halves and x equals 8. Alright, so this is how I can factor using my calculator. So an app in the calculator, and you can use this on the SLL, that allows me to factor. Okay? So it pretty much gives me, and if we go back to this step, this first example here, it gives me this step here. It gives me what x equals. So I'm starting at x equals when I use my calculator to factor. Alright? So now I know what x. So I'm starting at x equals, and now I know once I have these x equals, this is where my graph is undefined. So this is where the equation is undefined. Which means I can use these to find my domain. My domain is all real numbers such that x does not equal where it's undefined, which is x equals negative 5 halves. And x also does not equal, this will equal here with the dash through it is not equal. X is not equal to 8. Okay? The other thing is it also tells me my vertical asymptotes. My vertical asymptotes are exactly where my equation is undefined, so x equals 5 halves and x equals 8. So that's how you can use your graphing calculator to factor, and then use those factors to get to your domain and vertical asymptotes. Alright. Okay, so 9 we did for F we did in class. I'm not going to go over that again, but basically you just factor. Well, okay, so I'm going to factor my denominator. So I want to find where my denominator is equal to 0, so that I can find where it's undefined, so that I can then find my domain and my vertical asymptote. So this is a difference of squares. You can use a calculator for this, but you would just put in 0 where you have your b. But it's easy just to factor because the squares really fast. So minus, and then square root of 49 is 7. Alright, so I set these both equal to 0. These are my factors, so I'm going to have 3x plus 7 equal to 0. And I'm going to have 3x minus 7 equal to 0. And this will tell me where my vertical asymptotes are and what my domain range is. So minus 7, 3x equals negative 7, divided by 3, x equals negative 7 thirds. And then here I am going to add 7, 3x equals 7, divided by 3, x equals positive 7 thirds. Okay, so and now I know where my graph is undefined. It's undefined at negative 7 thirds and positive 7 thirds, which means my domain is all real numbers such that x does not equal where it's undefined, so x is not equal a negative 7 thirds, and x does not equal a positive 7 thirds. Okay. And space here, but bracket there. And then also my vertical asymptotes are x equals 7 thirds and x equals negative 7 thirds. Vertical asymptotes. Okay, so there's that one. Okay, so let's move on. Okay, I'm not going to do all these, I'll do some of them. So B, let's start with B. B is pretty quick. Alright, wherever my denominator is undefined, or wherever my denominator equals 0, so take my denominator, x cubed, is that equal to 0. X cubed, solve for x. Technically I'm taking the cube root of both sides, but those cancel. So just x equals cube root of 0 is 0. So my graph is undefined at x equals 0, which means my domain, they are all real numbers, such that x does not equal where it's undefined, so x does not equal 0. And then my vertical asymptote is x equals 0. Alright, so then let's do this one. Let's do A. So again, where it's undefined is where x equals 0, or sorry, where my denominator equals 0. So I just take each of my factors. I have 2x minus 7 equals 0. And then I take x plus 5 equals 0. And I see a solve. So add 7 gives me 2x equals 7. Divide both sides by 2. Then we move that 2 over. Leaves me with x equals 7 halves. also, I need to move this 5 over, and x equals -5. So my graph is undefined at 7/2 and -5, which means my domain are all real numbers, such that x does not equal where it's undefined, so x does not equal 7/2, and x does not equal 5. Okay? And my vertical asymptotes are x equals 7/2 and x equals -5. Right? Where it's undefined are where I have vertical asymptotes. Okay, so then we'll go on to, let's go to C. Again, I need to factor this before I can solve it. You can either factor by hand or factor using your calculator. Either way, you should get to factors of x plus 9 times x minus 2. And then I take my factors and set them equal to 0. So x plus 9 equals to 0 will give me where my graph's undefined, and x minus 2 equals 0 gives me where my graph is undefined. All right, so then x equals a -9, and x equals +2. My domain, all real numbers, such that x is not equal where my graph is undefined, so x is not equal to -9, and x does not equal +2. Okay, vertical asymptote. Exactly where my graph's undefined, so x equals -9. We said it was undefined right here and here, right? So it's undefined, so my graph has a vertical asymptote, x equals -9, and x equals 2. Okay, last one. Again, use your calculator to factor this. If you do, you'll end up with factors of, well, actually, your calculator, if you factored this for real, you would end up with factors of 3x plus 1 and x minus 5, which you would turn into zeros, and you'd solve for x. You get x equals 1 -1/3, and x equals +5. Now, if you were to put this in your calculator, the denominator, right here, your denominator in your calculator, you would get straight to this step right here. It would give you what x equals. It does not give you your factors. Okay? If you put in your calculator, you get straight to your zeros or where your graph is undefined. Okay, so now I can solve where my graph is undefined. I'm gonna come down here so I don't mess with this stuff. But where my graph is undefined, I know my domain does not include those values. So my domain includes all real numbers except where my graph is undefined, which is x equals -1/3, x does not equal 5. Okay. Domain includes all real numbers except for where it's undefined, which is also where it has vertical asymptotes. So my vertical asymptotes are x equals -1/3 and x equals 5. Okay. Okay, so okay, let's go over graphing. So graphing. Okay, graphing. We're gonna do this one kind of quick. Quick thing when you're graphing, couple things. Start with your. Let me erase some of this so there's no space. Actually, I'm not gonna go over this one. We did this one in class, so I'm gonna not go over this one. Let's go on to the rules for horizontal asymptotes. Okay, there's 3 rules for finding horizontal asymptotes. All right, horizontal asymptotes. The first rule. I'll write down the rules and I'll explain each example that corresponds to that rule after I write down the rule. So the first rule is we have a smaller degree on top and a larger degree on bottom. Now remember, a degree of a polynomial is its largest exponent. Okay? Degree equals the largest exponent. Necessarily the first exponent you see, but it is the largest exponent. So, I have horizontal asymptotes, my smaller degree divided by larger degree. Then I have a horizontal asymptote, which I'm going to abbreviate as HA. Okay, so HA stands for horizontal asymptote. I have a horizontal asymptote of y equals 0. Now notice, My horizontal asymptotes are always y equals something, whereas we have been talking about vertical asymptotes, which were always x equals something. So if you go back a page and look at our vertical asymptotes, we always said our vertical asymptotes were x equals something. Okay? Okay, so first rule. So let's look at one that has that. First rule. So let's go down here to this example A. A and then also C is another example. Right? So my degree on top is smaller than my degree on bottom. So my degree on top, if I don't see it, it's a 1. Okay, largest exponent is a 1 divided by 2. So it's a smaller divided by a larger. Okay? If it's smaller divided by a larger, then my horizontal asymptote is always y equals 0. Okay? Same here. Okay? I don't have an exponent on top, or my largest exponent is a 1, I guess. My largest exponent is a 1 over a 2. So it's smaller over larger, so my horizontal asymptote is y equals 0. Okay? We talked about in class how to find these on your graph. If you want to talk about that more, please continue. Okay, so the next rule, if it's the same degree on top as it is on bottom, same degree, I'll put the same degree over same degree. Same degree. If it's the same degree, then your horizontal asymptote, you know what? So same degree on numerator as it is in the denominator. Then your horizontal asymptote is y equals, horizontal asymptotes are always y equals, and so your leading coefficient. Now remember when we've talked about leading coefficients before, it's not necessarily your first coefficient, it's the coefficient on your term with the largest exponent. Okay? Leading coefficient over leading coefficient. Alright, so let's do one of these. So same degree over same degree. Let's look at B. We have a largest exponent, our degree is 2, over a denominator with a degree of 2. So it's same degree over same degree. So my horizontal asymptote is going to be my leading coefficient. So it's 4 divided by the coefficient in front of that x squared is a 1. So my horizontal asymptote is y equals 4 divided by 1, which is really just y equals 4. Okay, my horizontal asymptote. Alright, last rule. Green, we have larger degree divided by a smaller degree. So larger degree in the numerator, smaller degree in the denominator. My horizontal asymptote is y equals, again, horizontal asymptotes are always y equals, right? Or you don't have one. No horizontal asymptote. Got carried away with my y equals there. Okay? No horizontal asymptote. There isn't one. We don't want to have that one. Remember, we've done tons of graphs this year where we don't have any asymptotes. Alright, so let's look at D. Alright, my degree in the numerator is a 3, and my degree in the denominator is actually, I'd have to FOIL this out, which would give me a 2x squared. Basically, actually 2, but either way, my numerator is a degree of 3, my denominator is a degree of 2. So that means I have no horizontal asymptote. Okay, because my degree in the numerator is larger than my degree in the denominator. Okay, last thing we're going to talk about. Holes in graphs. Holes in graphs, what they are. All they are. Sometimes you have graphs that look like this. We might have like, let's just pretend we have like a horizontal asymptote at x equals 1 or something, I don't know. And say we have a horizontal asymptote on the x-axis at y equals 0. Okay, so then say I have a graph that looks like this, and a graph that looks like this, but then right here at like x equals, say this is at x equals 5, there's a hole. Okay, this means that's a value that whatever this relationship is, whatever this graph is graphing, x equals 5 is not valid. X equals holes. 4.999999 is valid. X equals 5 is not valid, right? That's what a hole is. Okay? Now, how we find holes algebraically is if the numerator and denominator have a common factor. So your numerator and denominator have a common factor. So let's do an example of this. Okay, so the rule is if your numerator and denominator have a common factor, this is what gives you. Okay, so an example. If we had x squared plus, well, sorry, I'm going to leave this little photograph. Looks like with a hole. Alright, example. If we had x squared plus 2x minus 15 divided by x minus 3. Alright, well, I have to know my factors to be able to even decide if they have common factors, right? So first thing I need to do is factor my numerator. If I factor this, I get x plus 5 times x minus 3 all over x minus 3. Notice I have a common factor. Okay, I have an x minus 3 in the numerator and an x minus 3 in the denominator. When I have a common factor in the numerator and the denominator, that means I have a whole. Okay? So I have a whole where x minus 3, which means I set this equal to 0, and so I have a whole of x equals 3, right? I just solved for 3 by adding that 3 over. So I have a whole at x equals 3. Now you have to be careful because remember at the very beginning of these notes we talked about vertical asymptotes. And vertical asymptotes, we found them by looking at our denominator, and we set our denominator equal to 0, we solved. But wherever our denominator was undefined, we said that was a vertical asymptote. Well, you have to check, because sometimes it will look like a vertical asymptote, but really it's actually a hole. Okay? If it also has that same factor in the numerator, it is actually a hole, not a vertical asymptote. Okay? That's holes. Right, so on the next page are the rest of these. We haven't gotten through these in class yet. We'll go through them next time, but we've covered all these topics. We just haven't pulled it all back together in these graphs. So here are the notes for them. I'm not going to go over them right now because we are going to go over them in class. But yeah, so this will give you a good overview. This lesson, almost kept under 30 minutes. We started with definitions of rational functions or expressions. Then we talked about finding domain for rational functions and vertical asymptotes. Talked about factoring on our calculator here in green. Then we talked about more vertical asymptotes. We talked about horizontal asymptotes and holes. So the main part of these notes were vertical asymptotes, horizontal asymptotes, and holes. Okay? So that's it for these notes, and I will see you in class next time. Don't forget to do your homework.